Hi, our first exercise is this one. Suppose a program that receives two numbers and returns the sum of these two numbers, and they are integers as I can see there. Numbers are between 1 and 99, and this is an inclusive boundary. So the first thing we should do is to first analyze the types of inputs and outputs that we see in this program, right? And that's what I'm trying to do here in these variable types and ranges. By types, I mean the type of the input. It's an integer as the requirement says. And the range is if there are limits for this input. So the program doesn't really specify names for this input, so I'm calling it x and y. So giving names is something very common to do when you're doing black box testing, because you don't have access to the source code, right? You don't know how the developer named those things. So it's normal that you give names to things. So x is the first number, it's an integer, and it has this 199 range. The same for the y and the sum. So note that I'm also analyzing the output, right? Because the output can also play a role in the tests we devise. So it's a sum, I'm calling it sum, it's an output variable, it's also an integer. I'm not putting a limit here, although we are bounded by the 99 plus 99. I'm going to put it here from 1 to infinity, but we could close this boundary a bit more. Then the second thing I tried to do is to analyze if those variables have dependencies among each other. And the first thing I see is that x and y are independent. And by independent, I mean that the value of x doesn't really influence the range of y. What do I mean by that? Let me give you a concrete example. Let's suppose we have x. Yeah, and x has to be between 1 and 99, right? We know this already. And we have y, and y is also between 1 and 99, like the program says, but y has one more restriction, which is y needs to be smaller than x minus 10, or something like that. So x influences the range of y, yeah? So this makes y dependent on x. This is not really the case in this exercise. So x and y are independent, and x and y are both used to calculate the sum. So note that I also try to see the relation of the variables with its output. Then let's do some equivalence partitioning analysis together with boundary analysis. This table here is also based on the Sam Kainer's book that I showed you before. And for now, because they are independent, so I'm going to do this analysis for both of the variables. And let me start with x. So first, the valid equivalence class, which is any number between 1 and 99. Then invalid classes. So we know that for x, numbers that are smaller than 1 or greater than 99 are invalid. And if I look at this equivalence class that I have, I can see basically two boundaries, right? The one that is closer to 1 and the one that is closer to the 99. So we can do the on and off analysis that we saw before. So 1 is the on point, right? And the off point is then 0. And for the other side of the boundary, 99, and the off point is 100. Great. So if we actually count, we now have 1, 2, 3, 4, 5, 6, 7. So we saw 7 different things to test for the variable x. Then we repeat the same for y, and they are very similar, right? So the same equivalence, valid equivalence class, so from 1 to 99. Those are the two invalid classes, smaller than 1 or bigger than 99. And the boundaries, 1 and 99 are on points, 0 and 100 are off points. Then, great, I did the equivalence partitioning and the boundary analysis. Now it's time to derive tests. And I need a strategy for that. And if I look at it, I see that x has 7 partitions, right? 7 classes that I want to test. Y also has 7 classes that I want to test. And the first strategy would be to just combine them all. Yeah. So all combinations, which is then 7 here times 7 here, 49 different combinations. That seems a bit too much for me. This problem is not so complicated, but then I also know that x and y are kind of independent, right? They don't depend on each other. So why would I need to do all the possible combinations? Maybe I can reduce it, given that they are independent. And if I do this, this means I could have 7 tests for this, plus 7 tests for this, and I end up with 14 tests. And so how do I do it? Well, what I can do is I just exercise the partitions or the classes for x, and I have to pass y. So for the y, I just pass an in point. I can think of any in point. There are many suggestions to choose in points. For example, some people suggest you to choose varying in points, so that at least you add some variability in there. This is quite aligned with the principles that we discussed before. Another strategy is choose a value in the middle of the range. So from 1 to 99, maybe 50 is around the middle there. So maybe that's also a good in point. And then that's what I do. So I first start with x, and I write 7 tests for the x. And if you see, they really match what I have in here. So first an in point, whatever they are. Then one for an invalid class, I put there 100. Then one for greater than 99, 250. Then 0, 1, 100, 99, and 100. So these are my first 7 tests, and they exercise the 7 classes that I devised before, and then the same thing, but now focusing on the y, right? For the 7 classes that I saw for the y. So 14 tests, and it seems I exercised everything I wanted to exercise here. And so I can ask you some questions now. So what do you think? Do we need test 3 and test 7? Because if you think about it, both exercise a number that is an out point, right? The difference is that in here I chose the off point, and in here just, an off point, and in here an out point that is really far from the boundary. Do we need both, or are we just happy with this one? That's a question that you as a tester should ask, right? Should answer. Is it worth to have this other test? Does it bring results for us or not? Yeah? So that's it.